Hey everybody, it's Mrs. Harbin. Last video notes, here we go. Brought up a song from some of your past. I know you're all dancing in the gym right now, but we're also going to get down to chemistry. But we'll be together for this last video notes. So here we go. Alright, so make sure you read section 16. It covers the buffer part of this. There are lots of cool things in chapter 16. Gum that foams, carbonation, a cool trick, plants fight back, airplane rash, and garden variety acid-base indicators. All that stuff's in your book. I suggest reading it. The buffer part is going to be, you'll be responsible for. The other stuff's just pretty darn cool. Alright, titrations, neutralization. Titrations is a technique. Neutralization is a reaction between acids and bases. Okay, so this is a neutralization. What that means is that an acid plus a base should give you water and salt. Now, not just table salt, but any kind of salt that comes from the acid and base. So let's look at it. These are double replacements. Okay, hydrochloric acid, you should be able to write the chemical formula for that. It's aqueous. And potassium hydroxide, K has a +1, OH has a -1, KOH. Salt and water. Well, it's a double replacement, so the water is the H2O part. It's a liquid. And the salt is the potassium with the chlorine, +1, -1 periodic table. Get it? Got it. Dissolved in water. Check to see if it's balanced. 1H, 2H, 2H is 1O, 1O. Balanced chemical equation. It's a neutralization because it's an acid and a base. Another acid, sulfuric acid, H2SO4, +1, -2, you need 2 of them. Sodium hydroxide, Na+, OH-, +1, -1, NaOH. Aqueous, reacts to formed. Let's do the salt first this time. We have sodium and sulfate. Sodium's a +1, sulfate's a -2. So we need sodium, sulfate. Get the correct formula before you move on, and then H2O is pure liquid. Now, 1 sulfate, 1 sulfate, 1 sodium, 2 sodium. You need 2 sodium ions, 2 hydroxides, so it's 2 O's and 2 4H's, so you need 4 H's and 2 O's. So, cancel charge first, balance with coefficients. Another neutralization reaction, because acid plus base gives you water, water is neutral. Now, in general, we're going to do that if it's a strong acid and a strong base. That's what's going to happen. HNO2, nitrous, comes from nitrite. Nitrite is NO2 negative. With the H in front, cancel the charge. Calcium hydroxide. Calcium's a +2. Hydroxide's a -1. You got to be able to do those. We'll get water again. That'll be liquid. And then calcium is a +2, nitrite is a -1. So we got calcium nitrite. That's aqueous. And then we have to, so this cancel charge first, then go back and balance. Let's see. Need 2 nitrites. It's giving me 2 H's, 3 4H's, 4 H's. Okay, these are called neutralization reactions because they're acids and bases. They make salt and water. Okay, so that's the actual chemistry. What do we use it for? We use it for a technique called titrations. I keep saying that, technique. So what's the technique? Well, you have this thing called a burette. Right, this is another burette, a burette. And it measures volumes to the 100th place. So it's pretty accurate. When you're going to do a titration, you rinse the burette with the substance you're using because you want it to be, you know, all the stuff you're using. You fill it with the substance you're using, and you open this called the stopcock. So this is open when it's up and down, closed when it's perpendicular. Parallel is open, perpendicular is closed, and then you let a little bit run out so there's no bubbles in here. Okay. Then in here you put in the solution you're testing, and you put an indicator. Okay. Add an indicator and put a beaker or flask below the burette. Record the initial volume in the burette. Add from the burette into the flask or beaker until you get the color change of the indicator just slightly. Okay, slight color change that stays permanent. So slight but permanent. And then you read the final And so then you have to subtract those two to get the volume of that added. Okay, initial, final, subtract, subtract. Okay, so titration is a technique. And so what's it going to tell us? Well, here's what it's going to tell us. Why does the color change? Well, when the acid equals the base, a certain pH is reached. We have indicators that change color at different pHs, so there was a lot of colors from that indicator lab. Equivalence is when the H plus equals the OH minus. Why? Because that makes water. And how do we know they're equal? Because when the moles of H plus and OH minus come together to make water, and then it neutralizes, that means they have equal moles. Okay. The equivalence point is when those things are equal. The end point is what you see as a color change. So you know that's when this happens. Equivalence is when that happens. End point is a color change. Okay, so how are we going to calculate something about our acid or base? Well, when the moles of H equal the moles of OH minus, hydrogen equals hydroxide, we know that it's equal. That's the equivalence. So how do you get moles? Well, we're going to be using molarity. Molarity equals moles per liter. So if you multiply moles per liter times liters, you get moles. Okay, so this is going to be moles of acid and moles of base and the volume of the base. So when is H plus equal to OH minus? When the moles of acid times its volume, molarity of the acid times its volume equals the molarity of the base times its volume. That's when moles of A equal moles of B, and that's the equivalence point. So here's a formula we can use. Now I can rewrite that formula, MAVA, and then H plus equals MbVbOH minus. Okay. Molarity of the acid, volume of the acid, the number of H's. X is H's for acid, the number of H's in the acid. So HCl has one H. H2SO4 has two H's. Okay. And then X for the base is the number of OH in a base. NaOH, one OH, MgOH, two OH equals 2. So you plug that in there. Okay, so it's kind of like the dilution equation, except because we want moles of acid to equal moles of base. So here's what it looks like. Here's your burette. Here's your flask or beaker with whatever you're trying to titrate. See how the color changes slightly? When the amount of moles coming from here equals the moles in here, that's when the color change is going to stay, and so that's the equivalence point. All right, so here's a problem. Okay, we have 0.25 molar sulfuric acid, so the molarity of the acid is 0.25 molar. Okay, and it's H2SO4. What is the volume of the acid? Well, 25 milliliters, 0.025 liters. How many H pluses are in the acid? 2. Okay. Titrated with 75 milliliters of base. 75 is the volume of base, 0.075 liters. Molarity of the base, concentration, that's what we're looking for. And then OH minus. How many OH minuses? Sodium hydroxide, NaOH. So 1. I almost wrote 2. There's only 1. Okay, so let's figure out what that is. So the molarity of the base is going to be equal to 2 H's times 0.25 molar H times 0.025 liters of H over 1 base, OH minus, times 0.075 liters of base. Liters cancel, molarity stays. So you plug that in and you get 0.166 molar NaOH is the concentration of the base. Alright, and just to double check, I'm going to plug it in my calculator. 2 times 0.25 times 0.025 divided by 0.075. That's what I got. Now, after the 6 was a 7. 2 sig figs, 2 sig figs, 2 sig figs. So I am going to make it 0.17 molar. Okay, so that was the concentration of the base we didn't know. All right, let's try it again. 25 milliliters of HCl. HCl. Volume of acid is 0.025 liters. Volume of base, 0.035 liters. I'm just trying to sort out the info. 3 molar molarity of the base, 3.0 molar. All right, so molarity of acid, that's what we're looking for. H plus. Well, HCl has 1 H, 1. OH minus, 2. Okay, so now we have to solve for Ma. Ma, the molarity of the acid, is going to be equal to 3 molar, 2 hydroxide ions times 3 molar times 0.035 liters divided by 0.025 liters times the 1 hydrogen ion, 1 mole of hydrogen ions. Okay, so 2 times 3 times 0.035 divided by 0.025 goes 8.4 molar HCl was what the concentration of the acid was. All right, so let's just go back. Titration is a technique based on acid-base neutralization reactions, and when it's titrated, the equivalence point is when the acid moles equal the base moles. How can we do that? Well, we need to know the molarity and the volume, the number of H's in the acid, the number of hydroxides in the base. What if something is more than 1 hydrogen? Okay, well, we've been showing hydrogens coming off 1 at a time. OHs actually break off two at once, but that's something like MgOH would have 2 breaking off at once. Okay, but here are 2 different Ka values for carbonic acid. The first one is a Ka for the first hydrogen breaking off, and then the second one is a Ka for the second hydrogen and carbonic acid dissociating. So what's the trend? Well, the second dissociation shows that this acid is a much weaker acid than this acid. Okay, this happens at a much smaller rate, not rate, but a much less than this happens. O3 negative. Okay, so this dissociates into that, and that dissociates into that, but then this is a very small amount at equilibrium because it's to the negative 11th. Okay, let's see if that happens again. Okay, it's the first ionization, second ionization. You can see that the second one is much less than the first. The trend is second ionization is much less. Okay. All right, buffers. Buffers are something that resists changes in pH. So it's a system of chemicals that resists a change in pH. Okay, so it's a combination of, so in a system you have a weak acid and its conjugate, or you have a weak base and its conjugate. Okay, so what does that mean? Well, that means here's HF, acid or base, acid, stronger, weak, weak. Okay, NaF, how is that? What is it? NaF is really a source of F minus. So this is a weak acid, and this is its conjugate base. So they're all in the same container. All right, same container. So you got HFs, you got some H plus and F minus because that's what an acid is, and then you got some more F minus. What else is in there? Well, there's sodium ions, but they're just spectating, or there's what they're called, spectator ions. They're just kind of watching what's going on. So 1, 2, 3, 4, 5 F minuses and 3 NAs. That means 2 of the F minuses came from the weak acid, and the rest of them came from the sodium fluoride. So what happens in this equilibrium system to make it a buffer? Okay, well, if I have this in equilibrium, then I have HF turning into H plus, yeah, it's equilibrium, H plus aqueous plus F minus aqueous. Right? What if I add more acid to that? Well, adding more acid pushes the equilibrium that way. Okay, now what else I have in solution is extra F minus floating around there. So if I say, let's see, let me put it this way. If I had some F minus, okay, and I added some base, sorry, wrong one. So if I add extra acid, it'll shift this way to push it that way because it'll be extra F. But if I added this, all right, if I add a base, if If I add more H plus, it'll shift that way to keep control of pH. But if I add more base, like hydroxide, well, hydroxide, all right, hydroxide, OH minus, will take away this and shift this way, right? Which is okay too, because there's extra F minus to keep this from going up too much or going down too much. So these F minuses help keep this from going up or down too much. And then if I add acid to this equilibrium or I add base to this equilibrium, it shifts either way based on what I'm adding, and then the F minus, extra F minus keeps this pH regulated. Okay, there's a buffer system in blood. Your blood has carbonic acid and the hydrogen carbonate ion in it. Okay, so because if you add more acid, one of the things picks up the extra H plus. If you add more base, that shifts away from that. You can keep the pH in your blood constant. Okay, pH of salts, NaCN reactions. Okay, so if I put, how did NaCN become NaCN? Well, if it came from a strong base, it would be NaCN. Okay. This came from HCN, so NaOH plus HCN makes NaCN plus H2O. Okay, well, let's look what happens. This is a strong base. This is a weak acid. All right, so when you form NaCN, this Cn minus is the conjugate of a weak acid. It's a conjugate base of a weak acid, so it's actually a pretty strong base, so that this solution right here is going to be a basic salt. Now you might be saying, what does that mean? That means if I take NaCN and dissolve it into water, then it should have a pH higher than 7. Why? Because it came from the combination of a strong base and a weak acid. And let's look at this. HCN makes H plus and Cn minus. All right. So which side of this equilibrium is favored? Well, this side. This is a weak acid, which means this is a stronger conjugate, a strong conjugate base. So that means the equilibrium pushes that way. So if I have NaCN in solution, I get Na plus and Cn minus. Okay. Then the Cn minus will react with H2O to form some hydroxide ions. Okay, I know that was roundabout every way, but I just want to let you to listen one more time to the explanation. So K2SO4 comes from KOH and H2SO4. All right, so KOH is a strong base, H2SO4 is a strong acid. How do I know? Because I memorized them. And I get K2SO4, cancel charge, and H2O. All right. So strong base and a strong acid react to make this. So K2SO4 will not have a stronger part of it than either of the acids or bases that made it. So it's going to be a neutral salt. Okay, because it came from strong acid and strong base. Okay. Aluminum nitrate comes from aluminum hydroxide, okay, and nitric acid. Now you're saying, how do I know that? Well, I know this part, the cation has to come from a base, and the anion has to come from an acid. Okay. So I'm going to get aluminum nitrate and water. Okay. Oh yeah, I do have to go back and balance these like that. And this one, it would be 3 of those. And 3 of those, 6, 3, 6, yes, okay. So anyway, so this came from a weak base and a strong acid, so this is going to be an acidic salt, okay, because the nitrate, the nitrate part of it came from a strong acid, but the aluminum part came from a weak base, so the strong acid would have a weak conjugate base, and the aluminum would be a strong conjugate acid. Okay, so that's why this is an acidic salt. Okay, so what did we learn? Salt from strong acid and strong base make a neutral salt. a neutral solution. Salt dissolved in solution. Coming from a strong acid and a weak base, you're going to get an acidic solution. Okay, and that is, the salt is acidic. And then coming from a weak acid and a strong base, you're going to get a basic solution. And that is a basic salt solution. Okay, weak and weak is unknown because it depends on how weak the weak base was and how weak the weak acid was, because they're not equally weak. Depends on their Kas or Kbs. Okay, so ranking acid strength. Which acid is the most powerful? The acid that's the most powerful has the highest Ka. That means it has the most ions. More ions means more dissociation. More dissociation means strong. Okay, a powerful acid has a weak conjugate. Okay, what conjugate base is the weakest base? Well, if this is the most powerful acid, then that's the weakest conjugate base. Weakest conjugate. So on this, okay, that's the weakest conjugate. Okay, so H2PO4 negative. What conjugate base is the best base? So which conjugate base is the strongest base? Well, here's the weakest acid. How do I know it's the weakest acid? Because the Ka tells me it has the least number of ions at equilibrium. So most of this sticks together, which means that this is the strongest conjugate base, because it stays dissolved and doesn't push to that side. Okay, so what is the trend? The higher the Ka, the weaker conjugate. Okay, lower Ka equals stronger conjugate. So you have to think about a lot of stuff in that one. Okay, so let's review together. And then remember that an acid and a base give you salt and water. That's the neutralization reaction. We use neutralization for titration. Memorize this formula and what it means, because that's the calculation. Buffers are weak acids and their conjugate bases, or weak bases and conjugate acid. Okay, they help control pH. So you have all of that in solution. The pH does not change. Okay. Now, big Ka, strong acid. Big Kb, strong base. Strong acid, strong base, neutral salt. Okay. One strong, one weak. The strong one wins. All right. Strong wins. And just to review, it's been super great working with you all this year. Okay. Make sure to read chapter 16 because there's some cool things. All right. Make sure you can do all that after this. And I want to say Boxing Hippo and Popeye Cow are hanging out at North, where you'll be for the whole day next year, most of you. Make sure to stop by room 315 after school, say hi. Shout out to Jen Grissom, because without her, there'd be no Boxing Hippo. Thanks, Jen. And without getting too sappy on you, had the best time teaching this year. And I look forward to when you take organic chemistry as a senior. Peace out. For good. Thanks, Herbs.